Good evening. Welcome back to, welcome to Kopernik Observatory. My name is Drew Desker. I'm the director here. And we have had just a fantastic AstroFest 2024. It's starting last night with just a bumper crop of people, and it's continued into today with some great workshops, a lot of good conversation, and it continues. So at this point, I'm going to let us go straight to our presenter, Tim, right? Tim Roprosky and Roski. I apologize. And we'll be doing a talk on astrophotography, and you're getting a sense of the kind of work he's able to do. And my guess is, with a little work, you could do it as well, right? That's the goal. All right, so Tim, if you want to come on up, we'll get you started. Also want to welcome those watching on the live stream. Again, for those of you that are watching on the live stream, or you can always watch this again. If you go to our YouTube channel, it'll be on there in perpetuity. And so if you missed, or you want to go back and review what Tim was saying, or what Lou will be saying later on this evening, go back to that video. So anyway,
okay.
Tim, it's up to you.
I'm on. I think I'm on. And can you hear me? Okay. So my name is Tim Roski. I am a longtime photographer. I was in the news business for about 30 years, and including at the Binghamton Press for a few years back in the 80s. And I got into this astrophotography business about 2015 when I heard there was a comet up in the sky, and I thought, well, wouldn't it be nice if I could see that comet? Well, I couldn't see it, and I said, well, maybe my camera will pick it up. So I put it on there, and I took a snapshot, and there was this little green blob in there, and I said, well, what do you know? I said, what do you have to do to get that to actually come out like those comet pictures I see? Oh, well, you need this and that, this equatorial mount, and you need, oh, what's an equatorial mount? And you have to know all about your sensor and all these different software programs and everything. And I dove into it, and it was confusing and frustrating. But one of the things that I find that's just fun is to do the Milky Way. And so I think they build this talk as wide field astrophotography, but let's just call it extra wide field astrophotography, because most of these pictures were taken with a 10 millimeter lens or a 16 millimeter lens. And I think the longest focal length is probably like a 50 millimeter lens for this purpose. Now I do have the whole thing with the telescope and the stuff that you might have heard about earlier in the earlier talks from maybe Patrick, with the deep sky and the little tiny nebulas and stuff. So I guess I have a slideshow explaining a workflow and how people should at least try it with whatever gear you have. You should try it. But I'll just this is pretty quick. So this is at Stellafane. I've seen a lot of you at Stellafane, and I know Kopernik sends a delegation. This is up in the Adirondacks. I'll just call it an undisclosed location. Same place, just as the Milky Way has moved over. These were all taken with a DSLR camera and a wide-angle lens. Most of them I use image stacking, which I'll explain, but you can get fine results without doing that. This is Cape Cod. This is in Vergennes near Lake Champlain. It was at an Airbnb we stayed at. This is a stitched panorama of the entire visible Milky Way taken in the spring at Cape Cod. Same undisclosed location. This is Star Trails. It's aimed at the North Star, and I just let it take exposure after exposure, and then stack that together in Photoshop or whatever. I live in Albany now. I'm actually from Vestal. I went to Vestal High School, graduated a long time ago, and but now I live in the Albany area, and we have star parties at that barn, the Octagon Barn. This is this clubhouse at Stellafane, and this is a dock of one of the camps at the undisclosed location. And this is at the Adirondack Observatory. The Adirondack Sky Center has every fall has a astrophotography workshop, which I just got back from last week. where Art was there, and that's how he caught up with me and knew I was coming to AstroFest anyway. So he said, "Hey, can you help me out?" So we were teaching. This is Cassiopeia, taken with like a 50 millimeter lens for several hours, and then stacked up in software. And this is a friend's house that he built. Nope, we got to go back. Okay, photographing the Milky Way. My hope is that you'll at least try it. I don't think tonight with all the moonlight, I think it might be difficult, but I'm hoping at some point that you'll take your camera, whatever camera you have, and put it on a tripod. I have my rigs here that we can talk about later. So the Milky Way, I think everybody knows the Milky Way is our galaxy, and it's as far as we can tell from surveys from like the Gaia telescope, we can presume that it's a barred spiral, and we are. I think we're circle. There's a little circle here for the sun right there. Whoops, wrong button. So the Milky Way, I was going to say now a word from our sponsor, because you can't see the Milky Way if you don't have dark skies or clear skies or if the moon is up. So maybe you've seen this before. This is from the International Dark Sky Association for your use and to promote this with your neighbors and friends, to use light only where it's needed, and so that it's targeted, so that it only falls where it's needed, and no brighter than necessary, and controlled with a motion sensor. So if it doesn't need to be on all the time, then don't have it on all the time. And the warmer color lights are better for our health, apparently, and also it's a little easier to filter them out when you're doing photography. They have filters that will get rid of some of that light pollution, where it's not able to get rid of the broadband spectrum LEDs. So dark skies are essential, and so keep working towards keeping the areas that you have control over dark. So it's fun to sit out there looking at the stars, but you'll look at the Milky Way and you'll see it there. It's just a faint glow. And part of the reason that it's faint to you is because the aperture of your eye is only, at my age, it's at most 5 millimeters. When you're young, we lost the young people, but then they have a little bit wider aperture so they can see better at night. But cameras, you can have a very large aperture on a camera, and the telescopes out there have apertures of 6 or 20 inch. I think the one is a 20 inch. So that collects a lot of light. The camera, the other thing about your eye and your brain is that you're only able to process about a 50th of a second worth of photons. So it's like when we're looking around, it's like watching a movie at about 50 frames per second. But in order to pick up the faint nebulas and stars, we need longer than that. So the camera lets you take a photo for, these Milky Way shots were mostly taken at 10 or 20 seconds. But when you're talking about these deep sky faint nebulas, you can go hours or even days. And one of the other parts is you can share your photos and get other people to appreciate the beauty of the Milky Way and the way that you have created your art, because it's the processing aspect of making your photographs is an artistic endeavor, I think. We're not out to capture, or I'm not out to capture a scientifically authentic photo of the Milky Way. I'm trying to bring out certain things and call attention to certain things so that the composition flows in an artistic and colorful manner. So the Milky Way is all around us, and we think of the Milky Way as just that brightish ribbon that goes across the sky, but the Milky Way is actually everywhere. most of the stars are here, but some of them are still there. So I have this picture here that shows the difference in seasons, why it looks different. So in the summertime, let's see if this works. So in the summertime, we're here, and at night, we're on the night side of the Earth. We're looking this way towards all this bright stuff and lots and lots of stars. And in the wintertime, when it's night, we're over here and we're looking out. There's a little bit less going on. But there is good stuff like Orion and Cassiopeia and Perseus, and it's still very good and very enjoyable. If you're going to do photography, you might, and a lot of the Milky Way photography involves having a landscape in the foreground. You can just take a picture of the sky. That's great, but this will help you plan where is the Milky Way going to be. When is the center of the Milky Way, that big bright part that comes up in the summer, that has all that nebulosity and dark lanes, and when is that going to be up above the trees? So you can use these apps on phones or PCs. I use Sky Safari a lot. It has telescope control and things like that I use for my other astro stuff. And PhotoPills is a fun one because you can hold your phone up and it will show you where the Milky Way is going to be at a certain hour, where you're standing. So the other day, my friend wanted to take a picture of her pool with the Milky Way. And I said, well, all right. So we were over there, and I took my app, and I said, all right, well, you're going to have to stand in this corner, and you're going to be looking that way, and at 8:30 p.m., the Milky Way is going to be right here. Then she closed her pool before we could do the shot. So the further away you can get from light pollution, the better. If you want to, for us in the north, that central part of the Milky Way is on the horizon. It's always low to us, and right now, by 8 or 9 o'clock, it's actually setting. So you want to be someplace where that's why water works so well, because you get a lower horizon, so you can see more above the horizon. The other thing you could do is go south, and if I had the opportunity to be at the equator this winter, and it was very cloudy, and I didn't get to photograph anything, but Orion was up there. So any clear night with a new moon is the best time. And a few clouds. You might have seen that one with the dock. There was a cloud off to the side, and I liked it. I thought the little glowing cloud added to the whole thing. The moon, I would say, this first quarter moon. Last night I tried to photograph here up on the hill in Vestal or Johnson City, and I could not make out the Milky Way over the moon, the moon glow, which was very close. The Milky Way was here and the moon was here. I couldn't see the Milky Way. So, but during a crescent moon, or before the moon rises, or after the moon sets, I'm not an early morning person, so I don't do that. But and the PhotoPills app also. It's a paid app, but it's a lot of fun. You can line up, you can actually it shows where the moon is going to be and how high up it's going to be relative to a location on a map. So this is where you get the church steeple with the great big moon right behind it. You could plan those photos that way. So going back to the time of year, in the spring, you can catch the Milky Way low on the horizon. And I have time lapses. This is not here, but where the Milky Way just goes up through the night, and starting in like the end of February, it'll be 4 o'clock in the morning. The Milky Way will be up like that, and then as you get into May and June, right after sunset, the Milky Way will be like that. So I think I shot that in May, and that's also a panorama. So it was multiple panels, 3 or 4 panels that I stitched together. And then in the summer, when the sun doesn't set and it doesn't really get dark until 9:30 or 10, by the time the sun sets, the Milky Way is going like this. So you get lots of opportunities for different compositions, and so you need a camera, and for a camera could be, I think for this type of photography, the DSLR or the mirrorless camera works great. A phone, I'm not sure where I put that. No. I have another picture later that shows some Milky Way that was taken with a phone. I just got a new phone like 2 weeks ago, and I haven't had a chance to try night stuff, but it has a night mode and it has manual capabilities so that you could do longer exposures, which the longer exposures are the key to all of this. You need a tripod, and no matter what you do, it's probably not going to be all that great right out of the camera. So you're going to have to take it into an editing app. So wide-angle lenses make it easier. The wider the lens, the easier it's going to be. You don't have to worry about the stars streaking, and you're just going to get a whole lot more, and the flaws aren't going to show as much in a wide-angle picture as if you were zoomed way in going, oh, why is that star funny shaped? They call it pixel peeping that people do with their astrophotos. So with the phones, my new phone has a night mode. It has manual. So those are two things that I think are really useful for doing this with your phone. I'm getting ahead of myself with the tripod thing, but this is just a little clamp, and I have it on I have it actually attached to my tripod head. But this clamp holds the phone, because handheld is not really going to work. You might see the nebulosity, but your stars are going to be all over the place. So I have this little bracket, which came with this. It came with this little flexible tripod. I found the flexible tripod is a little bit flimsy for holding this phone. So I'm probably going to, if I do phone photography, I'm probably going to put it on one of these tripods. A full frame camera is lovely if you can get it, but I don't have one. The only one I have is very old, and it has a lot of noise going on in it that the newer ones don't have. But the newer ones are expensive, and I guess there's no way around that. GoPros have my GoPro has a night lapse setting. I haven't been very happy with it. It does shoot the pictures, but under really dark skies, nothing comes out. I think it would be better when maybe you see some of these shots where there's a harbor, and the harbor has some light, and there's a little bit of light pollution, and then the Milky Way is visible above that. I think it would work well for that. But I think in a totally dark scene, I don't recommend the GoPro. Here's the alleged shot from smartphones. So the Samsung Galaxy S23, which is the one that I just got. I got the 23. It's the lower end model, and the iPhone 14. And this was on Reddit, and unedited 30-second exposures. So if this is true, that's a great starting point from a phone. And I'm looking forward to trying it with mine, because it's not always convenient to carry all this stuff around all the time. But if you can set your phone down and lean it up against something and get something like that, it could be a lot of fun. Lenses for our purposes, wide-angle lenses. I have a 10 millimeter 2.8. Does everybody understand like f-stops and focal lengths? Anybody have a problem with that? Okay. So I have okay, so the 2.8, the smaller the number, the wider the aperture of the lens, the more light gets in during any given amount of time. So the lens that I've been using the most is this 10 millimeter f2.8, and that allows for 15 or 20 second exposures without star streaking, and so I'll more about that later. They call them prime lenses, fixed focal length lenses. They can be a little bit sharper than zoom lenses, and they can often be a little faster, meaning they'll have a wider aperture available. And then the 50 millimeter, like this is a zoom. This is a 16 by 80, 16 to 80 zoom. Once you get up into 50 millimeters, you're better off putting it on the star tracker for reasons I'll explain in a minute. You definitely have to have a tripod. None of these 15 second or 20 second exposures are going to work handheld, and you could kind of lead it on something, but you're going to be frustrated. You're not going to be able to adjust the composition. My wife, who's here, says that carbon fiber is diamonds in the rough. So that tripod over there is carbon fiber, very lightweight and stiff. And if you wanted to hike up a mountain or something like that for your gorgeous Milky Way shot, so you can show me what it looks like up there, then then those are good. This is the one that I've had from my professional work since the late 80s or 1990s, early 90s. And then I showed you the bracket for the. The other convenient thing is the geared head. So when I was out the other night photographing the aurora, I was trying to get my horizon straight. So just a little simple turn of the knob straightens it out, or turns it this way, azimuth, altitude, and tilt. Very easy to adjust and sturdy, and it stays there. I find the ball heads are pretty frustrating. You loosen them up, and then things go too far, and you spend more time fighting with your ball head than capturing your image. Editing apps. My advice for us here is, if you have a photo app that you know how to use or that's intuitive to you, start with that. I really like Lightroom and Photoshop. I don't like Photoshop, but I really like Lightroom, and I use Photoshop with a lot of frustration and brain pounding headaches. But these are the things that you're going to need to adjust in your software, and these can be a phone app or a PC or a Mac. You're going to need to adjust the brightness, the contrast. In Lightroom, there's this clarity adjustment that really helps bring out, that I've found just a little adjustment to that really makes parts of the Milky Way pop. And I also use masks. If you would like, that would be like the next step up. You get your picture the way you want, but you can also use a mask to only adjust parts of the image. So a good one for a single Milky Way shot might be just a big circle, a nice soft circle where you can darken down some of the light pollution on the horizon without affecting the upper part of the photo that's probably dark already from the way your lens vignettes a little bit. You need to use manual. But it's easy because you're going to have your lens wide open to that, whatever the widest aperture is, and you're going to set your shutter speed to 8 or 10 or 15 seconds. Usually you can, on these cameras, you can select that, and on my new phone in the Pro mode, you can set 30 or 15 or 10 or whatever. So you're going to set one of those. The ISO, I'm not going to try to explain what ISO is, but the higher the number, the more gain that the camera applies to the photons that come in. So it's going to say, one photon came in, well, I'm going to count that as 2, if you put it on some of these higher ones. So it'll brighten the image. it'll also brighten, it'll also show the noise because you don't have the signal to noise ratio. Next step, don't worry about that. And raw images are the file format. In a Nikon, they're called NEF. CR2, I think, is Canon's. And all the camera brands have their own name for the raw images. These are uncompressed, so they have more room to stretch the data out and bring up the shadows, and they don't compress them and throw away data in order to make the file size smaller. So the file sizes are bigger, but they're more useful for editing, especially night photography where you're trying to bring out things that are barely visible. So for the shutter speed, you can use this as a rough guide. It's called the rule of 500. I call it the rule of 300 because I have a crop sensor camera. And then I tend to go even a little bit less than that, less seconds than that. So if you take your lens, so if you have a 24 millimeter lens, you take you go 500 divided by that 24 millimeter lens equals about 20 seconds that you could expose before the stars start to streak across the frame. I find I like to go a little less because I'm a little fussier. I am a pixel peeper when it comes to my photos. So I go a little bit less than that. This is fun. Focusing in the dark when your camera won't autofocus on the stars because it's too dark. So you have to use manual focus. And phones have manual focus, although I have found my phone in the night mode will autofocus quite well on the stars. I don't know how it does it, but it does it better than my Nikons. So you have the live view on your camera. Come on, there we go. So you have the live view on the camera, and you look on there and you find a pinpoint little star, or if it's not a pinpoint, you focus till you see some kind of star, and then you zoom in. There's a plus on this camera. There's a little plus button, and I can zoom all the way in on that little star, and then I can very carefully turn the focus ring until that star is as small and sharp as I can get it. The bottom tip is you're probably aiming at the horizon, but Vega and Deneb and all those are up here that are going to be easier to focus on. So you might have to just start out by focus on the stars up there, then compose your shot. So this is an example of what that would look like. It's probably going to look like the one on the right when you're viewing it live. And then after you take the picture, then you can zoom in and you see these, you see a little bit of streaking going on there. But that's when you're zoomed in all the way. When you zoom it out all the way to here, that little streak is only this big. So you don't need to be too fussy about it. So now you're going to push the button. And but don't just push the button. If you set a timer, a self-timer, you can push the button, then the vibrations can settle down, and then it takes the picture. And I have on, I have it on over here. I have this is called an intervalometer, and I can trigger the camera once just with the regular button, or I can set it up to take, and I'm going to get into this, I can set it up to just keep taking 15-second exposures until I tell it to stop. And I can just walk away and go sit in the, what I did with the Aurora the other night, I set it to shoot a time-lapse movie, and then I walked away and I got in the car and stayed warm in the car. So then, this is where we're going to get into the next level, which is the stacking. So if you shoot one single shot, you get 15 seconds worth of photons. If you take 10 shots of 15 seconds, now you've got 2.5 minutes worth of exposure. Or maybe you want to keep going and you get 5 minutes of exposure. Some of these deep sky pictures are hours and hours and hours of exposure to pick up that nebulosity. So, but if you can get with these cameras, if you can get 3 minutes or 5 minutes, you're going to find that you can bring up that signal so that really dim stuff starts to show and the not so dim stuff starts to pop. So this is one that I took last weekend. I guess it's not from the same series because the building moved. This is the Adirondack Sky Center's roll-off observatory. This one on the left is a single 20-second, I think, exposure. And it's pretty cool. There's a lot going on there. I should just confess here that that camera over there is a modified DSLR. It has a hydrogen alpha, a filter that allows hydrogen alpha to go through, and which helps bring out the nebula. That's the North America nebula. In the summertime ones, you may have seen a bright red nebula, and that was the Lagoon Nebula. So I am picking up a little bit more color than you might with an unmodified camera, but you can still get a lot of the ones that I showed you there were taken with an unmodified camera. So this is, I think, 40 of those 20-second shots stacked together in a program that I'm going to show you, that I'm going to introduce you to. I'm not going to tell you how to do it, but I'm going to introduce you to this program that will help you combine all of your images into a nice stack that keeps the ground stationary and stacks the stars together, even though as over the course of this the stars were going across the frame like this from the Earth's rotation. So going back to the single exposure, these are a lot of the tools that I apply to most of the photos these days. Most of the Milky Way photos, I apply these tools. Color balance. My Lightroom has an eyedropper tool, so I can pick a part of the background that I think is supposed to be neutral, and I click on it, and magically a lot of those color casts disappear. You can slide the magenta versus green slider, the blue versus yellow. The tone curve helps a lot, and I think I have a picture of the what I mean by the S curve coming up. The clarity slider is fun, and then the masks. So this is, I think, this is the single exposure, and that is, this must be after I use this eyedropper here to set the color balance. So I clicked in here somewhere in the sky, and it's set that to be fairly neutral. Then I raised up the exposure, and I think I had to bring the highlights down because the building was starting to get a little bit overexposed. And there's some clarity. The clarity slider, I moved that up quite a bit. So they're just these sliders are so fun because you don't have to know what you're doing. You can just go like this. Hey, I wonder what this does. Slide it all the way over and look at it. That's how you'll learn how to do it. This is a mask. So this lets you adjust. This is a linear gradient mask. So going from it affects it more up here and less down here. Because I think I want it to lighten up. Because I want it to lighten up where it's really dark at the top and make the sky just a little bit more even. And so then this is that S curve I was talking about in the undertone curve. And all you do is you take the left side represents shadows, and the right side represents the lighter areas. So you just bring those shadows down just a little bit, and then you bring up the highlight or the midtones. And I wasn't being picky when I did this. I was doing it just to show what an S-curve is. But now you can see that the Milky Way is starting to pop. So for stacking Milky Way photos, I use a program called Sequator. The equivalent for a Mac is called Starry Landscape Stacker. They are both fairly intuitive, but the other day I totally missed a step. So I was wondering, why is my ground all blurry? It's supposed to be, my ground is supposed to be stationary. So this is just a screenshot. You would load all of your star images. So all of those, that 20 pictures of 20 seconds that you took, you would load them in here. It's going to pick one in the middle time-wise. It's going to decide, when it does all the alignment on the stars, it's going to pick that middle shot and say, okay, I'm going to align these ones that were where the stars were over here. I'm going to move them here. All the stars that were here, I'm going to move them over here. And then this is the important part, is you want to align stars and you want to freeze the ground, which I didn't get to yet. There. Whoops. Oh, I'm touching the touchpad at the same time. So going back. So then it lets you draw. This is a mask tool. And all you have to do is tell this program where is the sky. That's all it wants to know. So you take this and you can increase and decrease the size of that with the scroll wheel on your mouse. You go around and you draw along the horizon, and then you fill. Now the program knows that this is sky. That's an airplane. And you tell it that you want to freeze the ground. And then when it all comes out, you'll get what you've already seen, which is a lot of Milky Way nebulosity, and the ground is still sitting there. The ones that I had in the slideshow, it actually accumulates everything. So everybody that walked by with a red light at Stellafane is in there over the course of that half hour or whatever that I shot. This is another thing that you can do. Star trails. I like aiming at the North Star because it makes this nice circle. This is Cape Cod, and this is Stellafane, the McGregor Observatory. And this is not difficult. You set your camera on the tripod. You set the thing to just keep shooting 15-second exposures or however long. You could actually do long. If you're just going to do star trails, you could shoot a lot longer. But with the same photos that you're shooting the Milky Way, you can combine them differently and get trails. You can do this in that Sequator program. There's an option for star trails, and you can also do it in Photoshop by changing. I'm just going to say this. I'm not going to try to explain it. If you open all the photos in Photoshop, if you import them from Lightroom, open in Photoshop as layers. Then in Photoshop, you go to layers and you change the blending mode from normal to lighten. And that will let all the light shine through all of the layers. If you got that, then you can come up here and talk next year. The other thing that's really fun, like I said, when I set this up and I go in the car and I sit there and get warmed up or whatever, you can then combine those into a movie. So this is probably 2 or 3 hours worth. It was a while ago, so I don't remember. But the same pictures that you're stacking together to make the Milky Way shot can become a time lapse if you have enough frames. I use a program called LR Time Lapse, which interfaces with the Adobe Lightroom. But there's a lot of ways that you could do it. The Adobe Premiere Elements is their consumer video software, and you could just import all the individual images in there and tell it to create a movie from that. Hello. This was what I was the stitched panoramas. So this is probably 10 20-second shots that I did for each panel. And then this is not easy. This doesn't always work because of clouds and light pollution and things. Just when you have this, there was quite a light glow over here that I had to tone down quite a bit in the processing. But to get all these, I finally had a nice low horizon and a clear night where I was able to finally get this shot a couple years ago. And I haven't been able to really do it since, or at least not this well. This is, for the next step, is to do tracking, and that is with a star tracker. This is my Skywatcher Star Adventurer, and what this does is it moves at the same rate that the Earth is rotating and follows the stars across the sky. And I have a little, this is my, I can show you, this is my, from my driveway, and you can see all my neighbors' porch lights. I think that's the moon, and so you can see what I'm working with at home. But I use narrowband filters at home to try to defeat that. But that gives you an idea of how it tracks through the night. And that's a much more sophisticated setup with computerized and all that. Let's see. So, but that would be the next thing. No. When we talk about the rule of 500, if you want to use a 50 millimeter lens or an 80 millimeter lens, now you're talking, I can only really get a 50 divided by, 500 divided by 50 is 10 seconds at the most. Well, maybe you're going to want, all of a sudden you're going to just go, I wish I could do 30 seconds or a minute or 2 minutes, and that's where the star tracker comes in, because then you can just continuously track it without streaking the stars. But it does take it takes extra setup. The beauty of the tripod system is with the shorter exposures is I like the view over here, and you can just move it. If you want to move that, then you have to reacquire the North Star and make sure it's aligned with the celestial North Pole every time you move it. So it would get pretty tedious. So this is this was with the star tracker with a 50 millimeter lens, and it's 2 panels stitched together. So one is like this, and the other one is like this. I shot this from the observing hill at Stellafane a couple years ago, and again, I just left it running while we were looking through telescopes and stuff, while this clicked away, and just kept tracking. And I think it's probably a half an hour worth of exposure for each one, and so it's kind of the next step, and it's kind of easing you into these big scopes on piers and all that. But it can be done with just a camera and an intervalometer. Yeah. That is, so this is the Rho Ophiuchi region. So you can see the color in there. I still have never gotten the Rho Ophiuchi the way I really want it, the way I've seen it, but I think it's because it's so low on the horizon for us in the north. I think I'm going to have to travel to get it really the way I want. This is the Lagoon Nebula. And this was the horse or something, I think they call that. And this is the pipe. It was in the Stellafane. Some of these were in the Stellafane Binocular Olympics. Yeah, dark nebulas. If anybody has a copy of that E.E. Bernard book, I'd love to see it. And then this one we had before, Cassiopeia. So we have, I think that must be the Pac-Man Nebula there, and the Heart Nebula, and the Soul Nebula. I saw I think that's the owl. I'm pretty sure that's the owl. But this was a couple hours worth with it might have been with the zoom lens, which might be why it doesn't look so sharp. But very short focal length, 50 millimeter, maybe 35 millimeter. And then I think my last one here that's Orion with a 50 millimeter. And so you've got the belt and the Orion Nebula, and you've got the Horsehead is over here. 50 millimeter lens on the tracker, and then using free stacking software. And I probably processed this in one of the Astro, specific programs, but you could get that result with Lightroom or whatever. We had a guy last week that was using Affinity Photo. He was having good luck with that. A lot of these are paid. There's GIMP, is I believe a free one, and I found on my phone. I haven't tried it with an Astrophoto, but just Google Photos, the editing on there, you can bring out a lot of details and fix things up. But anyway, that's me. I have a website with a lot of my there's an Astrophoto gallery on there, and among other things, I do drone photography, and that's my email if anybody wants to get in touch with me. And I'm plugging the Astrophoto workshop, which won't be until next year, but very good hands-on, one-on-one. We take you where you are at, and everybody walks out of there feeling pretty good and way more advanced than when they walked in. Anybody have any questions? Yeah.
If you have a question, I'm going to bring
Okay.
the mic to you, just so that they can hear it on the live stream as well. So I'll come to you, Keith. Oh, well, I'll bring it anyways. No, it's okay.
Well, thank you for this presentation. It's fantastic. I'm just getting into imaging. A lot of our guys here are big shots, really. But to see the wide field of those areas of the Milky Way, where we've imaged, or even Cassiopeia, we imaged the owl or the heart or nebula or the soul, and to see it all together, it's like, wow, that just opens my eye. Now I know sort of where to hop and look, and the detail of your stars and post-processing is sharp. And this is all done just with a full frame camera?
No, these are crop sensors. That this is they're both D5300s. This one has is modified to with a H alpha filter. I bought this camera used off of Cloudy Nights.
Okay, but so these are modified cameras. So H. So
right. So the hydrogen alpha. That's where this Barnard's loop here.
Yeah, I say it's Barnard's loop.
And the Heart Nebula. You can pick up the Heart Nebula without a modified camera, but it just takes more time. It takes more hours, I would say, to bring out the Heart Nebula than it does when the hydrogen alpha narrowband ability. There it is. It pops right out.
Yeah, they're just really neat shots. Well, thank you.
There's a book I just got. I was at NEAF last April, and I got a book called The Visible Universe. And it's for astrophotographers, and it shows different approaches of photographing objects. But one of the great things in this book is that the author and the authors they shot the entire Milky Way, and they have a gorgeous spread in the book, all in color, with the southern Milky Way and the northern Milky Way going across both pages. One of them versions is annotated, so you can see the name of all different objects that are in the book. And I love that picture. I would like to do the same thing.
Book title, what's it again?
It's called The Visible Universe. It's Charles Bracken. He's been coming to NEAF for the last couple of years. He has an astrophotography atlas, an astrophotography planner. He has several books out.
Any other? Oh, one here.
Yeah.
So theoretically, say I had some aurora pictures from a couple days ago,
Yeah.
and I shot them in RAW.
Yeah.
Basically, all you would do is, since they're not compressed, you would just basically denoise them.
Yeah, maybe.
hit the curves,
Yep.
maybe some blur,
Yep.
and that's it. You're basically done.
Yeah. For the aurora, I have a.
You didn't stack aurora pictures.
I,
right?
no, you don't stack aurora pictures because the aurora is constantly moving. So you want short. So for the aurora, you don't want to go over 15 seconds, because then you start to blur the movement of the aurora. And the ones I did have some blur of the clouds, but the aurora is still what you can see through the clouds is fairly sharp. But yeah, no, you don't want to stack aurora pictures. But again, I think that you can use artistic license, and if you want to make it look really contrasty and saturated, go for it.
But you would stack comet pictures, right?
Oh yeah, comet stacking is a whole other ball game. So I was hoping we'd get a view to the horizon up here tonight. So with comet stacking, you do the same thing, and you align all the stars, and then you have to align the comet head, because the comet head is moving against the background of the stars over time. So it's 2 alignment procedures, and there's a couple different programs that have comet stacking built into them to make it a little easier, but it's still complicated and a little time consuming.
We just had a picture sent to us of the comet from up in Massachusetts.
Mm-hmm.
Good 5 to 7 degrees.
Okay.
To the right.
If you can get it right, if you can get it with a single shot, great. I did some of NeoWise that were like 45 minutes worth, because I was trying to get the fainter details of the tail, and it was a fun job trying to get all of the stars to line up and the comet to line up on itself, and then the space station passed through the field of view while I was taking the picture. So I have the space station and the comet. And
All right. Any other questions before we wrap up? All right. Well, thank you so much, Tim.
so go out and try it. You might be surprised.
Absolutely. We can give a round of applause to Tim.
Thank you.
All right. So we are going to take a short break. Let's say 15 minutes. We'll get set up with the next presentation, and we'll be back. Let's see. That clock looks like it's wrong. Yeah. Let's call it about 8:15. Okay.
Hey, Tim.
Yeah.
So, I loved your pictures of the Milky Way, that it's like the naked eye.
Yeah.
Every time
Oh.
I see it, I'm like, it's like, this is just a blur.
I've seen ones
So
from.
I really
Okay.
like that you did that. But, so I guess part of me wonders, like, what is the range? Like, so you have the naked eye.
Yeah.
People don't put those out there.
They put the extreme.
Right. So I guess that's what I'm trying to find out from you. Is like, how can you do like a range and show people you're not going to see these beautiful things. You're going to see this blur of a line.
Good evening, everybody. Thanks for coming for our next program, and those who were here earlier, thanks for coming back. For those who don't know me, I am the president of the board of directors here at Kopernik. If you were at our gala last week, you probably saw me there. So again, thanks for coming. Our next speaker is Lou Mayo. He grew up in Springfield, Virginia, and lives in Newmarket, Maryland. Lou is going to talk to us about Titan, Earth's real sister planet. Just a little bit about Lou. He's a professor of astronomy at Marymount University, also president of Ares Scientific, a nonprofit dedicated to astronomy outreach, and program manager for the NASA Solar STEAM Heliophysics Outreach Program. And also something about Lou is, when he worked for NASA, he was quite involved with the Voyager missions, which are still going on. Unfortunately, he's not going to talk about that tonight, but that's also an interesting topic. But Lou? And you got the mic on, right? You got your mic on?
I don't.
Oh, okay. And I'll give that to you.
Let's see. We'll try it here. Does that work? Okay, great. Well, good evening. First, let me apologize for my disheveled position. I don't usually. I came to observe and stayed for the pizza. So. Right. So I always talk about Voyager, and no matter what I'm talking about, I spent 12 years on the Voyager infrared science team, and spent a good part of my career studying the outer solar system, most specifically Titan, Saturn's largest moon. We're going to talk about Titan today and the Saturnian environment, and I'm going to use some terms that hopefully you all will understand. The first is that we're going to be talking about large distances, right? So when astronomers work with large distances, they develop different size meter sticks, different size yardsticks, right? So you don't have huge numbers to work with, right? So we're going to be talking about large distances, like, well, I mean, some of them you're familiar with. I imagine you know what a light year is, right? Who knows what a light year is? What's a light year? Somebody tell me. Distance light travels in a year. No. A light year is just like a regular year, only it's less filling. Because it's a light, fewer calories for years. For the solar system, we're going to use our yardstick will be the AU, the astronomical unit, which was the holy grail of astronomy for centuries. How big is the solar system? And the AU is the average distance between the Earth and Sun, about 149 million kilometers, about 93 million miles. So we'll be using that. Anyhow, we'll come up with some other terms, and I'll just let you swim in them for a while. Glenda the Good Witch said it's always best to start at the beginning, right? So here's the beginning. Although Galileo was first to see the rings of Saturn, he didn't know what they were, right? These cup handles on the side of this planet. But Christian Huygens, back in the 1600s, accurately identified them as rings around the planet. And so no accident that the Huygens probe that went to Saturn with the Cassini mission was named after him. Then in the early 1900s, Jose Comasola observed limb darkening on Titan. Now, for those of you who are attending the talk last night, we talked about limb darkening on the sun. And this is simply a product of increasing optical depth as you scan down from off the planet onto successively thicker layers of atmosphere. Okay, so this is the first evidence that Titan had an atmosphere, right? In fact, a significant atmosphere. Then in 1944, Gerard Kuiper, you might recognize his name, the Kuiper Airborne Observatory was named after him, and he is the discoverer of the Kuiper Belt, where the short period comets come from. And Kuiper used spectroscopy to identify methane, or if you're British, methane, in the atmosphere of Titan. So not only now does Titan have an atmosphere, a substantial atmosphere, but it has methane, and methane is a biomarker. And so Titan zoomed to the top of the list of places that were interesting in the solar system. And of course, we've spent a lot of your tax dollars to go view Titan, and I'll be talking about some of those missions shortly. So let's just learn a little bit about Titan. Its diameter is about 5150 kilometers. That's about 3,200 miles. It has a surface, it's a very relatively small surface gravity. When we fly a spacecraft by it, we see that the orbit of the trajectory of the spacecraft is bent, but not by an awful lot. So its density is on the order of 2 to 2.5, somewhere like that, grams per cubic centimeter, which Earth's is 5.5. So there's a lot of water ice, that kind of thing, in the bulk composition of Titan. So as a result, its gravity is relatively low. Do we have a pointer? This thing here? There we go. This is important. Its surface pressure is 1.5 times Earth's. Okay, so with a not only is it higher surface pressure, but it's a much more extended atmosphere. So if you were on Titan, assuming you could weather the atmospheric composition and the cold temperatures, and you put on some wings, you could fly around Titan, right? But its surface temperature is kind of around 94 Kelvin all day, every day. Doesn't vary too much equator to pole because the atmosphere is so thick. So it's very efficient at spreading heat around the moon. Now, Titan, as the largest moon of Saturn, is 10 AU away, so 10 times further from the sun than the Earth. That means it receives about 1/100th as much light per square meter, right? And its dense atmosphere takes out about 90% of that, so only about 1% of that reaches the surface. So a bright summer's day on the surface of Titan would be kind of like a full moon at night here. Okay, not much. What we're seeing here, by the way, is from the Cassini-Vims instrument. And this is an instrument on Cassini that was designed to look through the cloud cover of Titan. So if when Voyager got to Titan, it could not see the surface because it's shrouded in a photochemical haze that is a result of the breaking apart of nitrogen and methane in the upper atmosphere, recombining into all these cool nitriles and hydrocarbons. But this is, and I'll talk to you about how we do this in a little bit. This is seeing through those clouds onto the surface. So right away we can see some features here. And it turns out, by the way, that these are lakes and clouds. And we'll be talking about those. Just get kind of a comparison, size comparison. Here are some of the major moons of Saturn. I don't know how many moons it has now. I think it's over 70. When I was in third grade, I gave a talk on the planets to my third grade class. And I drew with a colored pencil about what we knew about the planets on the front of the page. And then on the back, I had what I was going to say, right? And I was pretty nervous. But at that time, Saturn had 9 moons. Jupiter had 12, right? So we've come a long way. And I tell my undergraduate class that by the end of the semester, the universe is going to look very different than it does today, and it always does. Science is really marching forward in the field of astronomy and space science. So here's Titan, Saturn's largest moon, second largest moon in the solar system behind Ganymede, and some of Titan's other moons. The other moon that's of special interest is Enceladus, and that's because it has water ice geysers that have hydrocarbons and organics in them. And we've actually flown through those geysers with the Cassini spacecraft and collected some of that material and analyzed it with Cassini's mass spectrometer. So, very interesting, but we're not going to talk so much about Enceladus today. It's Titan, Earth's real sister planet, that we're going to talk about. So here's a nice picture of Titan taken from Voyager, and that's about how it would look from visible image, in visible light. Okay, the surface is absolutely obscured from kind of like Los Angeles type smog. Think of it that way. Okay, so it's got high altitude smog all over the place. Another size comparison. Here's Titan compared to the Earth and Venus. Venus is about 95% the diameter of the Earth. Mars is about half the diameter. Titan's a little smaller than that. So here, look, if Titan were orbiting the sun instead of Saturn, it would be a planet. Okay, I'm just preparing you because I will get questions about Pluto later, and so we can then talk about what a planet is. So it's actually bigger than Mercury, and certainly bigger than Pluto. So with all of this interesting stuff, we have sent a number of spacecraft to the Saturnian system and to view Saturn. The Pioneer spacecraft in 1973 to Saturn, Pioneer 11. Then the two Voyager spacecraft launched in 1977. And then 20 years later, in 1997, we launched the Cassini spacecraft with the Huygens probe that actually parachuted down through the atmosphere of Titan and landed on the surface, and we'll see some of those surface images later in the talk. So maybe we can just kind of walk through that a little bit. So the early robotic missions were Pioneer 10, which went to Jupiter, and then Pioneer 11, which went by Jupiter and actually took some data, some images and data, and then on to Saturn. These are flyby missions only, and they were, by our standards today, pretty primitive. But they got some of the first images of the outer solar system up close. This actually is the first image from a spacecraft of Titan. Okay, yes, that's Saturn, looking very great with the shadow of the rings and the divisions in the rings. Pretty low resolution, and there's Titan down there. Okay, we knew at that point we knew Titan was a fascinating object, and so we wanted to do as well as we could to get images of Titan and other data. This is the best image that Pioneer 11 was able to take. You're seeing photochemical haze. You're seeing the photolysis of nitrogen and methane producing this enormous prebiotic chemical soup of hydrocarbons and nitriles that the photochemists are just having a heyday with. And so I'll show you some of those models a little bit later. So very interesting. 1977, we launched the two Voyager spacecraft, Voyagers 1 and 2, and they were flyby missions as well. Voyager 1 went to Jupiter and Saturn only. Voyager 2 went to Uranus and Neptune as well. And the reason Voyager 1 only went to Jupiter and Saturn is that they sacrificed the rest of the mission in order to get very, very close to Titan, to get the highest spatial resolution images possible. That's how important Titan was. This is the flight path of the two Voyager spacecraft by Jupiter in 79, Saturn in 80 and 81, and then Voyager 2 on to Uranus in 86 and 89. And now, by the way, both Voyager spacecraft, traveling at about 3 AU per year, are outside of the sun's influence, outside of the heliopause, the edge of the bubble of the sun's electric magnetic influence that we live in. And they are in true interstellar space, the only human-made objects in true interstellar space. Here's a schematic of the Voyager spacecraft. You'll notice a few things. Here's a magnetometer boom. You don't want your magnetometers near the spacecraft because you don't want to measure the magnetic field of the craft. Radio science here. This is the communications antenna, which is used not only to communicate, but for science purposes. We did radio occultation experiments with it where we shoot a radio signal through the atmosphere from behind the planets, through the atmosphere, and look at how much it's deflected at Earth, and from that we can tell something about the temperature and the composition of the atmosphere. What else here? This is the scan platform. This is unique for Voyager. It's think of it as a wrist. Okay, so all the instruments that you want to point, the spectrometers, the imagers, you put on the scan platform, and it can move independently of the spacecraft so that they don't have to turn the whole spacecraft in order to point those instruments. And that's great, but it also introduced a little pointing error. And so, you know, little pluses, some pluses and minuses. So there's the scan platform. There's the IRIS infrared interferometer spectrometer that I worked with for so many years. Narrow and wide angle camera. Somewhere in here is the ultraviolet. Oh, I see they combined, and ultraviolet spectrometer there. And then a whole series of fields and particles experiments for detecting electric and magnetic fields and solar wind particles and that kind of thing. So Voyager got to the Saturnian system into Titan in around 1980, and here's what it saw. So what you're seeing here, again, is this photochemical haze. You're also seeing a division here, which is lighter on the bottom than on the top. That is not a solar angle effect. That is a composition effect. Titan orbits Saturn in 16 days. Very slow rotator. It's tidally locked to Saturn. So as a slow rotator, it doesn't have a lot of Hadley cell type circulation in its atmosphere. So instead of multiple bands of upwelling and downwelling air as we have on Earth and many more on Jupiter because it's a faster rotator, you have kind of wholesale movement of the atmosphere from one hemisphere to the other every half Titan year, which is every half Saturn year, which is Saturnian years, 29 and a half years. So if you're an astrologer, well, if you're an astrologer, meet me in the parking lot. I've got a few things to say to you. But there's something special about your Saturnian birthday, your 30th birthday, because they say then your life repeats or something like this. Some madness like this. You'll also notice some structure up here. This is the North Polar Hood. This is a real artifact. It happens in the south as well, half a year later. And this happens as the pole is tilted away from the sun. And so the chemistry of the atmosphere, because it doesn't have the ultraviolet radiation to break down some of the atmospheric composition. And so it kind of builds up, and you see this, what's called the North Polar Hood here. Very interesting place. I'll probably focus a little more heavily on some of the work that I did, but this kind of gives you an idea of what we did at Titan. These are the fields of view of the IRIS instrument as we scanned down from deep space onto the moon here. And these are the spectra that were taken as actually averages of 3 fields of view each time as we scanned further and further down. And so what you're seeing here is this just really exciting chemical soup with acetylene and ethane and methane and diacetylene and hydrogen cyanide and all these cool hydrocarbons and nitriles. This was important because it gave us vertical information, height information about how these gases varied in composition with altitude. I mentioned that I'd tell you a little bit about the photochemical models. Here they are. This begins with nitrogen and its many byproducts. This one begins with methane and its many byproducts. This was an early Voyager photochemical model, and I'm sure this has been revised since Cassini, but fundamentally it's accurate. So it's an exciting place because a lot of these things are kind of building blocks for life, such as hydrogen cyanide, right? And building amino acids. So it becomes very interesting, kind of shoots to close to the top of your list when you're going to spend tens, hundreds of millions of dollars sending a spacecraft out to somewhere, and Titan is certainly a high value target. And we're going to talk about not only the past missions, but a very exciting future mission to Titan. Before Voyager, this is what we had. I remember going to the Division for Planetary Sciences conferences, and we were all speculating what the surface might look like. Even after Voyager, because we didn't see the surface, we had ground-based images that looked through absorption features, methane absorption features in the atmosphere between like 1 and 2 microns. There are places of very low methane absorption where you can look right down to the surface. This is from the Canada-French-Hawaii telescope on Mauna Kea. And so we got some indication of what the surface was like. There's something there, there's something different there, and there's something different there. And so we were just, it's a lot of speculation that was going on. What could this be? We could watch it rotate with the moon itself. We had other models that suggested that this rich chemical soup, that some of this stuff at those temperatures and pressures are probably precipitating out like clouds, right? And not only precipitating out, but perhaps, and this is all done through modeling at the time, perhaps dropping out like rain. So maybe the surface has lakes. This was speculative at the time. Active radar measurements of the surface indicated that there were places where it was rather smooth. So it looked like, yeah, okay, maybe there are lakes. And so some of this modeling that I did with Bob Samuelson at Goddard and that Carl Sagan and Thompson did at Cornell and some other groups indicated that probably there are lakes of hydrocarbons on Titan, and that there's a methane cycle. We have a water cycle on Earth. Water clouds form, it rains, it pools, it evaporates, and the whole cycle repeats. Same thing happens on Titan, but at much colder temperatures, so it happens with methane. Yes, you have a question?
Yeah, so there, I'll say his name. Elon Musk, in an interview, said that an easy way to melt the polar caps on Mars would be thermal nuclear weaponry. And that would melt the polar caps. Mm-hmm. What are your thoughts on that?
He's an idiot. He's a brilliant idiot.
He's brilliant.
I suppose in theory you could do that. It's not going to do much for Mars. Right now we take pay special attention to clean our spacecraft super clean. So there's not even any bacteria on it when we send it to Mars, because we don't want to modify the environment. We want to see what Mars is, not what the Earth has brought to it. Set off nuclear bombs on Mars, that's going to modify it a little, okay? I tell you what, we will talk about a much better place to go than Mars at the end of the talk. I promise you. So you can see here that these images were taken in the 1 to 2 micron range, and that's where these windows between methane absorption features exist. Now for you amateur astronomers, here's a Cassini imaging subsystem image of Titan, again looking at the photochemical haze, not looking at the surface. And here's about the best I have ever seen from an amateur telescope. Of course, it's a very nice amateur telescope. It's a Celestron 14-inch edge and all this great equipment. And it's blown up a fair amount, right? But Titan from Earth at 10 AU, okay, 10 times the distance. I'm sorry?
I was talking like
okay.
See what AU was.
Astronomical unit, right? 10 times further from the sun than the Earth. Absolutely right. Subtends an angular size of 0.7 arc seconds. So that's going to test your equipment, right? So you're going to have a big aperture to do that. Anyhow, that's your challenge. Go get a picture of Titan from your backyard. There have actually been some papers written on how to observe Titan from, say, 8-inch Schmidt-Cassegrains from your backyard. Not just observe, but to do spectroscopy on it. And so you would use CCDs and a grating spectrometer to do that. I mentioned the windows between absorption features in the atmosphere. Here are those windows, and when you look in those spectral windows, you can see down to the surface with some clarity. So, at Voyager 1 at Titan, and also Voyager 2, not quite as close to Titan, we were able to get a fascinating view of the atmosphere, to identify its composition from the ultraviolet spectrometer, looking at atoms, right, which are emitting in the ultraviolet, from the infrared spectrometer that sees molecular vibrations, and also from radar measurements. Okay, so we were able to get a really good picture of the kinds of amazing chemicals that are produced in what we are calling a prebiotic atmosphere. Now, Carl Sagan up at Cornell was very interested in this, and he understood the atmospheric dynamics and the collection of material on the surface, and he called these tholins. Okay, and we had a partnership with the University of Maryland Space Science Lab, where they're actually able to make some of this stuff in the laboratory, and I was able to get I mean, they can't make a lot of it, but they have, I have a small sample of these photochemical tholins here. If I can see how this opens. You can see they're kind of dark, and have both hydrocarbon and nitrile composition, and they kind of coat the rocks on the surface of Titan, and they're quite tasty. So, Cassini at Titan. In 1997, the Cassini spacecraft with its Huygens probe launched from Kennedy Space Center, and it delivered the Huygens probe into the atmosphere of Titan. This is like, these are the people who I think are the real heroes of these missions. They can pinpoint a landing within, some few tens of kilometers, 1.5 billion kilometers away. It's remarkable. As Cassini parachuted down through the atmosphere of Titan, it had a downward pointing imager, and we got some of our first visible looks at the surface. And what we were seeing were, I remember we didn't know quite, they look like rivers, but we don't want to say rivers, so we called them fluvial channels. And you can see they look like rivers, right? And then some flat areas, and then some probably more mountainous areas. This a little bit here. This image is especially interesting. It turns out here are flow channels for the hydrocarbons that are on the surface. This is a lake. It's a hydrocarbon lake. And these are methane clouds. And I remember being at Cornell University at a Division for Planetary Sciences conference. And Bob Samuelson and I had done our papers. Sagan and Thompson had done their papers. The Canadian group had done their papers. The same data, I showed you that data, was scanning off the moon and onto the moon. The same data. Are there methane clouds on Titan? Bob and I said, maybe. Sagan and Thompson said, absolutely. The Canadian group said, no way. And it turns out that there are, in fact, methane clouds. In fact, there's methane supersaturation in the atmosphere of Titan. So this probe landed on the ground, and we suspected, strongly suspected, that the ground could be some form. It could be a sea. You could be landing in some liquid, or on a hard surface, or anything in between. So there's kind of a spring-loaded thing on the bottom of the probe. And if it did not compress, then it would be landing in liquid. If it compressed fully, it would be landing solid. If it compressed slowly, then it would be kind of marshy, and it turns out it was kind of marshy. So these are actual images from the surface of Titan. These, you can see the dimensions for some of these rocks here in centimeters. And also liquid on the surface here. So these are likely covered with these tholins that Sagan referred to. So we're seeing kind of a real nice combination of the kinds of surface features that are on Titan, but it's only for one location. So imagine if you landed a probe on Earth, if you landed it in a jungle in South America, you'd see one thing, and if you landed it in the desert in California, you'd see another thing. So you have to be a little careful. But nevertheless, this is real data and real images from the surface of Titan. From orbit, we can do a lot too. These are not real colors. This has been image enhanced to show more definition. But these are from the Cassini orbiter. These are lakes. These are all hydrocarbon lakes here near the North Pole, I think. Again, the Cassini VIMS instrument, the visual and infrared mapping spectrometer, was able to see through the methane absorption features and map the surface. So here are 3 images of the surface that kind of reflect the entire sphere of Titan. And once again, we see surface features, we see large lakes, and we see clouds. This is the radio occultation experiment that I referred to earlier. Cassini flew beyond Titan and then used its communication dish to send a radio signal through the atmosphere that was picked up at Earth, and the degree to which that signal was attenuated gives you a quantity of T over M, the temperature at that level in the atmosphere over the mean molecular weight. Now, one thing that I have not mentioned about Titan is that it's by far its primary atmospheric constituent is nitrogen, N2, right? So it has a molecular weight of 28. So we kind of know more or less the molecular weight. Therefore, you can get a pretty good temperature profile from that. Now, what's the dominant atmospheric constituent in Earth's atmosphere? Nitrogen, right? So Earth's sister planet. I'm making a case here. This is not just science. This is also law, okay? Think of me as making closing arguments. So science marches on. This is from the Voyager infrared interferometer spectrometer, the IRIS instrument, infrared spectrum of Titan. And this is from the Cassini Sears composite infrared spectrometer spectrum. And you can see that it's much higher resolution. The Cassini Sears instrument actually had 3 focal planes with various spectral and spatial resolutions, as opposed to the single focal plane that Voyager had. So it's 20 years further into the future, and somewhat better technology, and able to do a little bit more science. So from all of these observations, we build models. So here's a model of what might be happening in the atmosphere of Titan. We have solar UV breaking up methane and nitrogen, and we saw all of the amazing byproducts of that photodisassociation. Some of the modeling that we did also indicated that there are condensates. There's haze particles that are scattering light at it's about 90 to 120 kilometers, as I remember. I guess that's about it, about right here. It's kind of a log scale. So once we put in a single scattering model into our models, we were able to fit the data very nicely. So these things are condensing out here. You have ices in the atmosphere. Down in the troposphere, which goes up to about 40 kilometers, you have methane clouds and rain that settle on the surface, and then a methane cycle. We also, more recently, believe that there is volcanism on Titan, and so that contributes somewhat to the atmospheric composition. From all that, we can make some, I don't know what to call it, educated guesses, I suppose, about the internal Titan. We've mentioned the organic rich atmosphere and surface, some sort of an icy shell perhaps below that. This is the big one, the global subsurface ocean, either water or water methane mix. NASA has a program now, I think it's still called called Ocean Worlds. And we're finding that there are a lot of worlds in the solar system have subsurface oceans. Europa does. Europa Clipper's launching, is it tomorrow? Did it launch today? I don't know. Anyhow, a mission to Europa, subsurface ocean. Ganymede, most likely. Titan, probably Enceladus. So this is exciting because everywhere on Earth that you look for life, you find water, right? Everywhere there's liquid, put it this way, everywhere there's liquid water, you find life. So that's very exciting for the possibility of finding life outside the Earth. This is kind of a beautiful picture of the limb of Titan. Photochemical haze, detached haze layer up here. Just a pretty picture. So I like to show that. And this is a cool picture. This is sunlight glinting off a lake, a hydrocarbon lake on Titan, and then into the imaging systems of sensors. So that is light glinting off a hydrocarbon lake on Titan. Well, that's Cassini. And Cassini we had to send into the atmosphere of Saturn in order to make sure that it doesn't pollute any of the other moons, right? We don't have anything up close to the Saturnian system any longer, but we do have Hubble, we have JWST, and we have ground-based observatories. So here are some images from the Hubble Space Telescope Wide Field Planetary 2 WIFPIC camera. Again, looking through methane absorption features at the surface. And here we have the benefit of being able to do it over very long baseline periods. Okay, flybys, you get one look. Orbiting, you get a little longer look. And from Earth, you can look as long as you want. These are images from James Webb. No, I'm sorry, these are Keck. This is Keck. This is Webb. Forgive me. And so here we can see a little bit higher definition of some of the surface features, cloud features, and liquid features on the surface. So we've been there. We have looked there. We have telescopes still observing Titan, both visually and spectroscopically. What's next? This is a mission that is being developed by the Johns Hopkins Applied Physics Laboratory called Dragonfly. Dragonfly is in development now. I think it launches in 2027, if I remember correctly. This is going to be a drone that flies around in the atmosphere of Titan. It will parachute to the ground. Oh, I said I didn't have any videos. I do. We'll see if it works. We'll see if it works. Parachute to the ground. Communicate with the Earth. Remember, it's 10 times further from the sun than the Earth. So light takes 8.5 minutes to go from the sun to the Earth. So 10 times that. So you can't use a joystick to control the spacecraft, so it has a lot of smarts in it to figure things out for itself. It's an octocopter, so it has 8 blades, and a nuclear power source. Right? You're far from the sun, and you're deep in an atmosphere. You don't get much light, so you're not going to use solar panels. And it will fly around, look for interesting places to land, come back, land, report back. We'll decide where it should go. We'll send the command. It will then pick up and go look for other things. It will have spectrometers on board. It will have weather stations on board, so you know the wind speed and the atmospheric temperature and pressure. We'll be able to sense the composition of the surface as well as the atmosphere. This is an exciting mission. I mean, can you imagine? And so this will launch I think it launches in 2027, and it's about a 7-year mission, I think, to get to Titan. So you can go about your business and not wait right away, but it'll be a little while. I think that's right. Let's see if I'm right. 2034. Okay. Well, I don't think 2026 is right anymore. I think it'll launch in 27. Here's the orbit. A few gravity assists on its way to Titan. It will use aerobraking initially through the atmosphere and then drop 2 parachutes. Thick atmosphere, it's a lot easier to do than Mars. Right? At this point, it will sense the surface, the distance to the surface, and then when the distance is right, it will drop the aerocopter, and that will land on the surface. So this is what I was hoping it could do. Let's see if this works. I think it's going to work. Here's a video from the APL of the landing, what it should look like on Titan of Dragonfly. Hopefully a flat place. Right. So it will communicate with the Earth, tell it what it sees. We'll have a chance to think about it and send some commands to it. Periodically, and then it will go off and use those commands as well as its own onboard intelligence. I think that's the same thing. So, where's the young man who was here? I promised him something. Well, let's all take a 5-minute break. There's a very interesting paper by Ralph Lorenz and others, Chris McKay and Jonathan Lunine, on Titan under a red giant sun. So in 5 or 6 billion years, our sun will run out of hydrogen fuel, and then it'll run out of helium fuel. You're back in time. I promised you something. In 5 or 6 billion years, our sun will run out of hydrogen fuel in its core and run out of helium in its core eventually, very much quicker. And it will expand into a red giant, right? As the core shrinks and gets hotter, the outer envelope will expand. It'll become huge. It will engulf the orbits of Mercury, Venus, probably Earth, and possibly Mars. It's a bad day for the Earth. But it might be a good day for Titan. Remember, the photochemistry that happens in Titan's atmosphere happens with ultraviolet radiation from the sun, right? Breaking apart all the methane and nitrogen. Well, that's going to drop. That ultraviolet flux is going to drop. And so the atmosphere should clear up. And with such a large surface area, the sun has much more surface area to pump out photons, it should warm up Titan. Well, I already mentioned that Titan has a lot of water ice, right? It's frozen like steel on the surface now, but with all this heat and all this light and heat and energy and not so much atmosphere to obscure, the surface should warm. Perhaps there will be water lakes on Titan, right? And these other constituents are going to go back into a gaseous phase because it'll be too warm for them to condense out. So Titan may be the right place to buy lakefront property in the future. And if any of you are interested, see me after the talk, and I'll give you a good deal. It could be, yes. Some ROI. Okay, we have a financial investor. Yeah, that's right. So hopefully humanity will still be around and we will have left this planet and be exploring other worlds. But I wanted to make my point. Here's Earth, and what does Earth have? Well, it has poles and polar processes, seasons, lakes, rivers, volcanoes, water, nitrogen atmosphere. We have clouds and precipitation, a water cycle. We have smog, certainly. And we have biotic chemistry. And that's what Titan has. So I say enough of this talk of Venus being Earth's sister planet. I think Titan is Earth's real sister planet. And I'd like to do two promotions very quickly. One is for the YouTube show Space Oddities, which is on Tuesdays at 3 p.m. on YouTube. And it's a group of, an international group of planetary scientists, astrophysicists, and heliophysicists talking about what's happening in space, launches, anniversaries, new discoveries, that kind of thing. Tuesdays at 3, if you're interested in learning more. I'd also like to, is Art here? Art, would you stand up, please? Art Casiola has volunteered his time for the last 5 or 6 years in a program to work with Girl Scouts to teach them space science, teach them astronomy, and help them run their own astronomy clubs back at their councils. And Art was one of the amateur astronomers who was selected to work with the council group from, do you know the council? Say again? NIPEN Pathways Council. So Art has been doing that for a long time and making a real difference in the lives of these girls. This is a picture of our program. We brought them to Goddard Space Flight Center each year. We had a competition. 10 councils from around the country competed. And we gave them tours, we gave them lectures, we gave them star parties. We had them meet world-class scientists. And we taught them how to start their own astronomy clubs back in their councils. And then we gave them some telescopes and some support, like the support that Art gives his club. And so that has gone on. The funding is now gone, but Art still participates in our monthly telecons. And so there are still some clubs ongoing, and new girls are coming in and learning about space science. And every now and then, as I'm sure you do, Art, I'll hear about a girl who was a freshman in high school when she started and now is in college and wants to be an aerospace engineer or an astrophysicist or something like that. So making a real difference. Art, thank you very much. And I'll end there and take questions.
All right, if you have a question, I'm going to come to you with the microphone so the live stream can hear the question as well. All right, got one here.
Okay, so you brought up the point that when the sun combusts and turns into a red giant, it will engulf Mercury, Venus,
probably
Earth,
maybe
Mars.
We don't know.
And not Jupiter?
Don't think so.
All right. but that's when it turns into a red giant. So what and then you brought up the point that will heat Titan. What happens when the red giant becomes a supernova?
It won't.
It won't.
No, massive stars become supernovas. It will lose some of its material, right, as its core shrinks. And then after the red giant phase, it will slowly fade away into a white dwarf. And, that's about it for the whole solar system.
Yeah, then we all die.
But what a way to go on the shoreline of Titan. In other words, all this doesn't happen immediately, right? So perhaps that could buy us a few extra years.
All right, see you in 6 billion years.
See you then.
Any other questions from the audience? Got one from Mark back here.
Crashing a probe into Saturn, how do you know that that's not going to contaminate Saturn?
Well, it will. But Saturn is huge. I forget how many Earths you can put across Saturn, probably something like 8 or 9. Saturn is massive. It will make no difference whatsoever to Saturn. It will just consume the probe, and the tiny, tiny, infinitesimally small difference in the composition of Saturn will not be noticed by anyone. However, crashing into a moon, a tiny moon of Saturn, it might.
Speaking of the influence speaking of huge Saturn, what are there tidal forces that get involved on Titan? I've heard it said that the tides on Earth may have contributed to the ability of the chemistry to form life.
Yeah, it's probably a good idea that we have a large moon that produces tides, because there's some thinking that life began in small tide pools that were created by the pull of the moon and to a lesser extent the sun on the Earth. So Titan has a slight eccentricity in its orbit. It's also tidally locked to Saturn. That slight eccentricity will provide some energy, for internal energy, for perhaps keeping the subsurface, as you saw in the model, liquid. So that's what we know about tidal friction and Titan's orbit as a result of its being tidally locked.
Any other questions from the audience? One up front.
So you're talking about Dragonfly, the new probe that's going to, in the next few years. Is the thinking then that that's how probes are going to be deployed more, is with this, you're saying it's a drone or whatever, rather than just boom, plopping down? I mean, I'm wondering what the thinking is for all these other probes that they're going to be doing.
Right. So it depends on where you're going, right? So we have a drone on Mars. Now that's really hard to do, because whereas the Titan atmosphere has a surface pressure 50% greater than the Earth's, Mars' surface pressure is 1% of the Earth's, right? So it depends on where you're going. Obviously, just to point, if you're going to the moon, you're not going to try to fly around the moon with copters, because there's no atmosphere. So it depends on where you're going. Titan is the only, besides Venus, it's the only object in the solar system with a truly substantial atmosphere that you can land on. Of course, the outer gas giants have substantial atmospheres, but there's no surface. Right? So I think it depends on where you're going and what you want to do. On Europa, we don't want to fly. We'd like to dig down or melt down through the ice sheath to see what might be swimming in the ocean under Europa. So you would kind of tailor your mission to the conditions of where you're going.
I've got one more for you. All right.
Shoot.
So she brought up the drones, and you said that of course, they can't use solar energy because it's
Too far from the sun.
yes, and then you brought up how it will use nuclear energy.
Yeah.
Can you explain that to me? Because
Sure.
I have no clue.
Sure. The Pioneer missions, the 2 Voyager missions, Cassini, and in the future Dragonfly, all used what are called RTGs, radioisotopic thermoelectric generators. This is plutonium-238 that generates, I think it's alpha particles that create heat, and that heat is picked up by thermocouples, and those thermocouples turn the heat into electricity for the spacecraft. Does that answer your question?
Yes, sir.
Right. All right, I think that's all the questions. I didn't see any in the chat, so let's give another round of applause to Lou.
Thank you. Thank you.
Yes, thank you so much for delivering 2 of our keynote presentations this year at AstroFest, both incredible topics. I know I'm very excited to see Dragonfly on Titan in the distant future a little bit.
I'll be on the science education board for Dragonfly, so we'll be trying to design programs for the public to get interested in the mission.
Oh, fantastic. Fantastic. Keep
Yeah.
us posted for that.
We'll do.
All right. Well, that does conclude our at least presentations for AstroFest. Though we do have clear skies tonight again, 2 nights in a row. So venture out to the telescopes, to the observatory, and look at Saturn. Later on tonight, Jupiter and Mars will come up as well. Mars much later, but yeah, lots to see out there. And thank you all for coming to AstroFest. And thank you to those on the live stream as well.
All right. We'll give you back your